You've now seen an example of applying the dynamic programming technique to the problem of finding the correct parenthesization for a chain of multiplying matrices together. But what part of that was dynamic programming and what part of that was specific to that problem? Well, dynamic programming is a technique applied to optimization problems that at first look like they might take a lot of time, maybe even exponential time. So for example, in the matrix chain product, if we were to try and solve that just using a brute force approach by finding every possible different way that we could parenthesize that chain of matrices together, we'd see that that's actually that there are exponentially many different ways to do that, so we wouldn't be able to use that kind of an approach. However, with a dynamic programming technique, we can define our global optimal solution in terms of optimal solutions to subproblems. So this means that our problem has this subproblem optimality property. And more so, that the subproblems we define are simple, meaning that we can use just a few variables in order to describe them. So we use J to describe a subproblem in the previous example. And also, even though we might have a lot of subproblems, they're overlapping. They're not independent. And for that reason, we construct our solution bottom up, meaning we solve for smaller sized subproblems first, and then we use those solutions in order to give us solutions to our larger sized subproblems. So we use this technique in dynamic programming. And that's actually how it gets its name. So dynamic programming, this term, programming, doesn't come from programming like the programming that you know and love, like writing a function and then we program this function or something. No, this term programming actually comes from, this is referring to a table, like a programming on the TV. You have a table of all the different shows that are going to come up tonight. So programming here just refers to the fact that we maintain a table and we periodically update it based on our latest results. So this is what our dynamic programming technique is. We're going to see this applied to another problem now, the 0-1 knapsack problem. Remember, we had seen the 0-1 knapsack problem before when we were looking at the greedy method, and we saw that with the knapsack problem, we have a knapsack that has a capacity W. This is how much weight it can carry. Then we have a set of n items. Each item has a weight and a benefit associated with it. With the knapsack problem, we want to take all the items that we can so that we maximize the total benefit of the items that we have in our knapsack without exceeding the capacity of our knapsack. And there's two variations. With the fractional knapsack problem, we were allowed to take a portion of an item, and we saw that we could solve that using a greedy method. With the 0-1 knapsack problem, we can't take a portion of an item. We have to either take all of it or none of it. So this is our 0-1 knapsack problem, and we can't solve this using a greedy method. We need a different approach. As it turns out, though, we can solve this using dynamic programming. So in this case, we want to maximize the total benefit of the items that we end up putting in our backpack. So T represents the items in our backpack. But we don't want to exceed the capacity of our backpack. So how would we do this? So let's say, for example, that we had the following books. And we had our knapsack was just a bookshelf which could only hold a total width of 9 inches. So we can't take all of the books that we have, but we can figure out for each book how many inches width they have, and then also what the benefit is. And of course, our algorithm's book, this is worth the most. So how would we solve this? Well, we could try every possible input. So we could try every possible subset of books and check to see if by putting all of those books together that we check to make sure that we don't exceed the width of our knapsack, and then record how much total money we end up getting. And if we don't exceed the width of our knapsack and we have the most amount of money than any of the other possible solutions that don't exceed the width of our knapsack, then that would be our solution. But unfortunately, there are exponentially many different subsets of books that we could try. The reason for this, we could represent this as a bit string of length 5. In this case, of length 5, or if we have n books, this would be of length n. And we'll put in this bit string a 0 if we don't take that item, and a 1 if we do take that item. So for example, this bit string would correspond to the situation where we take item 2, we take item 5, but we don't take any of the other books. So how many possible bit strings do we have? If we have n positions to choose from, and in each position we could place either a 0 or a 1, so there's 2 options, then we've got 2 to the nth power number of possible solutions that we could try. So we can't use a brute force approach because this would take exponential time. So instead, we're going to try a different approach. So a solution for this problem would just be that we take item 5, item 3, and item 1. So this would give us the most amount of money that we could make our bookshelf worth, essentially. But how do we get that? Well, we want to define subproblems. So let's try first saying, okay, we'll take, of all of the items we have, here's item 1, item 2, all the way up until we've got n items, right? So let's put n all the way down here. We could try to define a dynamic programming approach to this by defining subproblems as, we'll define B of k as being the best selection that we can pick from just the first k items. So not considering all of the items, we'll kind of work our way up to all items, but we'll define bk as being just the best selection of not everything, but just from the first k items. So for example, if we had the following set, so this is the benefit and weight. So this item is worth $3 and it weighs 2 pounds. So for these 5 items, the best solution for the first 4 items would be we only choose from these first 4 items. So B4 would be the following set, assuming that our knapsack can carry 20 pounds. But unfortunately, if we were to define our subproblems this way, this doesn't have the subproblem optimality property, because we have this is the best solution for if we're picking just the first from the first 4 items. This does not give us an optimal solution for how we can pick in the best way from the first 5 items. So this is a global optimal solution for if our backpack can carry 20 pounds and we can choose from all 5 of the items that we have. This is what we would end up picking, the one which maximizes the total benefit. This is the first item in each pair. Maximizes the total benefit of all the items we take. However, this global optimal solution is not written with respect to the global, with respect to the optimal solution to this smaller problem of only picking the best out of the first 4 items. So the problem here is that we don't have enough information represented in our subproblem in order to be able to reuse it. So we need some additional information. So instead, we're going to try a second attempt here. So we've still got this parameter k, which indicates how many items we're looking at. Again, we can number all items from 1 to n and just use k to represent. We're only going to consider the set sk, which is the set of items numbered from 1 to k. So if we've got items 1, 2, 3 up to n, sk would be if we just take these first k items. So we're still gonna keep that idea that we only consider the first k items and kind of work our way up. But we're also going to keep track of how much weight we're going to consider, how much capacity we're going to consider. So we're going to look at the best solution, so B of k and w. This represents the best selection that we could choose if we can only pick from the first k items and we can't exceed capacity w. Now if we do this, the good news is this does have the subproblem optimality property. And the reason for that is we can define B of kw in one of 2 ways. So there's only two possible situations that could happen. Either when we get to this kth item that we consider, suppose we had already a solution for the best way that we could pick from the first k minus 1 items. Right? So we had already, for every possible weight, let's say we had already figured out, this was our smaller size problem, the best way to figure out how many items we could pick from the first k minus 1 items of any weight, of any capacity. We're going to use these smaller subproblems in order to help us figure out what a solution for, now that we introduce this kth item, how many items or which items we should take from the first k items if we can only carry at most w pounds. So the idea is either we take this new item k or we don't. So if we take this item k, then this is what we have here. If we took item k, then the total benefit that we end up getting is however much benefit we get from that item k, plus, now that we've taken it, we might still be able to take other items from the first k minus 1 items, but we have a limited capacity now. This is whatever our capacity was before, minus however much capacity we just took up from taking that item k. So we can use this solution, what we've already computed here, in order to figure out how much we would get if we took item k. Or if we don't take item k, this is what we have. So we have the option of taking as many items as will fit between the first k items. If we don't take item k, then our solution will just be however many items we could take from the first k minus 1 items, because we know we're not taking item k. We've got the same capacity here because we didn't put anything in our knapsack. So only one of these two things could happen. If we don't take item k, we have already our solution pre-computed. If we do take item k, we can use a pre-computed solution, but we have additionally now the benefit of item k to take into consideration. And note that in this case, we have to adjust what our capacity is because item k is taking up space in our backpack. So when will any of these situations occur? Well, if we don't have enough room in our backpack, meaning that the capacity that our backpack has is less than whatever the weight of that item k is, then we definitely can't take item k. If w is too small, that our backpack doesn't hold the item k, then we definitely can't take it. This is the first instance here. But if our backpack is large enough that it could support taking item k, then we have to decide which instance we should take. Either we don't take the item or we do take the item. Okay, so I'm going to show you an example of this first, and then we'll see in pseudocode how we would express this. So we're just going to use this characterizing equation, and we're going to consider, because we need, for the previous k minus 1 items, all possible kind of temporary capacities of increasing size backpacks, we're going to look at for if we can only just take the first item of all possible weights, and then consider if we can take the first 2 items of all possible weights, and the first 3 items of all possible weights. And we're going to use these smaller size subproblems to give us a solution to our larger size subproblem. Okay, so let's say now, so I just rewrote that characterizing equation above. Let's say we have a knapsack that can carry 7 pounds, and we've got the following 4 items to choose from. So we've got the benefit of each item listed here, and the weight of each item listed here. And the idea is we're going to figure out first, okay, if we can only take from item A, how much could we get? If our backpack holds 0 pounds, so I'm going to represent up above, this is how much our backpack can currently hold, our kind of temporary backpack. And once we reach the end, this will be our full backpack of what we're given, how much we can hold. So how much, if we can only take item A, how much could we make here? Well, item A weighs 1 pound, so if our backpack doesn't carry anything, we can't make any money. We can't put anything in there. But if our backpack can hold 1 pound, then we could make exactly $1 by taking this item A. because item A weighs 1 pound too. So here we can make $1 from taking item A. If our backpack holds 2 pounds, well, we can't take any more of item A. We've only got 1 pound to work with, and we don't have any other items at this moment to choose from. So the most we can make, even if our backpack increases in size, we can only make $1, and this is from taking item A. All right, now let's consider that we could take from the first 2 items. So now we're going to incorporate item B in there as well. So again, if our backpack doesn't carry anything, then we can't make any money off of that. Not a very good backpack. But if our backpack can hold 1 pound, how much could we make? Either we don't take item B or we do take item B. Because item B weighs 3 pounds, we actually won't get to do anything until we reach a capacity backpack that can hold 3 pounds. So all the way up until this point, we're going to use the same solution of what we had before of if we don't take item B, which is just in the cell above. So this is the best way that we can choose from just the first item A if our backpack can hold 1 pound. So this is going to have the same value. And this is that we don't take item B, we only take item A. Now here we get the opportunity to take item B, but we have to figure out, should we? If we don't take item B, we'll get $1. If we do take item B, we'll make $4, and then we won't have any room left over for anything else. Well, $4 is better than $1, so definitely we'll take item B. If we have 4 pounds that our backpack can hold, not taking item B means we only get $1. If we do take item B, then we get, let me put this over here actually, let's say, this is our table B, and this is our item B. If we don't take item B, so here's 1, 2, first item, second item. So for this cell, we're trying to fill in what's the best amount of money we can make, selecting from only the first 2 items, and our backpack can carry 4 pounds. You have to consider, if we don't take item B, we only get $1. If we do take item B, we get $4. Plus, since we can carry 4 pounds, but item B only weighs 3 pounds, we've got an extra 1 pound left over, which means we're going to look at how much we can get if we have, taking from the first item, we've got just 1 pound left over. This is what we solved here already. That means we can get $4 from taking item B, and then another $1 from taking item A as well, because we can carry both of them at this point. So we would get $5. And even as we increase the capacity of our backpack, the most we can make is $5. So we can recheck for each of these cells, but I'm just going to fill in knowing already that we won't be able to make more than $5. Okay, now that we incorporate item C weighs 4 pounds, so we won't be able to do anything new until we can carry 4 pounds worth of stuff. So up until that point, the best we'll be able to do is the best that we were able to do before, which is just taking from the cell immediately above it, because the cell immediately above it represents the best way we could select from the first 2 items carrying that specific capacity. All right, now we can hold 4 pounds. Should we take item C or no? If we don't take it, we get $5. If we do take it, we also get $5. So it actually doesn't matter in this case if we take it or not. We'll get $5 either way. If we can carry 5 pounds, not taking item C gives us $5. If we do take item C, we get $5 plus we can make an additional $1 for the remaining 1 pound that we would have left over, which means we would get $6. If we can hold 6 pounds, without taking item C, we would only get $5. But if we do take item C, we would get $5 for item C, plus, since this carries 6 pounds and item C is worth 4 pounds, we're going to check to see how much we could get from the previous items if we could only carry 2 pounds. So this means we'll get $5 from item C and then another $1 from the previous items. So this is still $6. And then lastly here, we could get $5 if we don't take item C. If we do take item C, we'll get $5 for item C, plus we'll have a remaining 3 pounds that we could carry. So we'll get $5 for item C plus $4 for the other items gives us $9. Okay, now lastly, let's see for item D. Since item D, to make this go a little bit faster, let's say item D, we'll keep this. Item D weighs 5 pounds. So until we get to 5 pounds that our backpack can carry, this isn't going to change at all because we won't be able to take item D, so this will just be whatever we had before. So if we're not taking item D. Okay, now that we can carry 5 pounds, what should we do? If we don't take item D here, we get $6. If we do take item D, we get $7. And then we don't have room for anything else, but $7 is better. And then here, if our backpack can hold 6 pounds now, without taking item D, we get $6. If we do take item D, we get $7, plus we have 1 pound left over, and we can get $1 out of that remaining pound. So that means we get $8. And then now we have our backpack can carry 7 pounds. If we don't take item D, we get $9. If we do take item D, we get $7 for item D, plus an extra $1 for the remaining 2 pounds that we had, which means we would only get 8 pounds if we don't take $8 if we don't take item D. So we'll keep the one which is better, which is not taking item D. So this gives us, this is the largest dollar amount that we could make taking from these 4 items, knowing that we can either take an item or leave it. We can't take only a fraction of an item. We could similarly, as to what we did in the previous solution for matrix chain product, we could similarly record along the way in each cell whether or not we took an item, so we could kind of work our way back to figure out which items we took. So in this case, we obtained this amount by not taking item D. We obtained this amount by taking item C, which means we used up 4 pounds of the 7 pounds that we have to work with, which means we have 3 pounds left over. And how did we get this amount? This was from taking both, from taking only item B and not taking item A. So here we took both item B and item C, and this is what gave us that $9. Okay, so notice that when we filled out this table, we only ever used the previous row, because we only need to know from the previous k-1 items what happens. We don't need to know for k-2 and k-3. We used those solutions already to give us a solution for working with the k-1 items. So when we write this, we're going to keep that into consideration that we don't actually have to maintain this entire table. We only have to maintain 2 rows at a time. So this is what we do here. We're given some sequence S, which has n items. We have a weight, capital W, which is the capacity of our backpack. And then we're going to, rather than maintaining that full table, just maintain 2 arrays. And this will keep track for us of the last 2 items, this BK and BK-1, since we don't need the remainder of this. So just like we did in the previous slide, we'll initialize for everything. If we have weight 0, then definitely we don't have to fill anything in there. And for our first array, if we don't take any items, we won't get any money. Then we'll work our way into filling out the next row, using what we had computed in the previous row to do so. And we'll calculate which should we do. Should we take item B, this is this instance, or we don't take item K, or we don't take item K. And whichever one of these gives us a larger value is the one that we're going to record in that next array B. And then we'll use this array B in order to help us form the next array, and so forth. So our total running time here is, we've got a for loop here which goes from 1 to n, and then a for loop which goes from our starting weight to capital W. We're working in integer amounts here, so we have for each possible weight from 1 all the way up until capital W, and we're not going to maintain all of these in storage, but we'll have for item 1, 2, 3, all the way up until n. But we only maintain the last 2 rows at a time, so we won't need that much space, but we still have to fill in each cell of this. And we've got n times w, capital W, many cells that we have to fill in. So this is our total running time, big O of n times w. So this isn't polynomial time because it depends on something other than n. This is pseudo-polynomial because we have this other dependency. But this gives us a way that we can solve, using dynamic programming, solve now the 0-1 knapsack problem as well. If you have any questions, post on Piazza, reach out and let me know.